How much time do you have? 30 minutes?
25 minutes.
25, okay.
Presentation and then discussion.
Okay, so this is the title. Doesn't work. This was just to show you, just to show Jarno a little bit of snow that we have also in Sicily last week, but on the other side we have the sea. So this presentation is very much similar to the last presentation by Luca yesterday night. It's very, very similar, so it's just a continuation, just some difference. So we speak about continuum dynamic mechanics. The difference are, the model here is thermodynamically consistent, starts from thermodynamic. There is coupling, possible coupling between plasticity and damage. It is compatible with the existence of an elastic nucleus for the material and has a clear threshold for damage or plasticity. It's based on internal variable, each one of which may have a physical interpretation, sound interpretation. It's very easy to implement in finite element codes. And the most important thing is that the constitutive equation can be solved locally, even though the model is non-local. So there are two papers about this subject. A little bit of motivations. This is a metamaterial. It's made with filaments of polyamide, and you know what it's used for? It's used in football fields, underneath the grass, because it's a shock absorber for the players who have to balance, yes, to bounce. And okay, this is one. Now, when this material has to be elastic, because but it can also undergo damage, because if the pressure is too much, the filaments are very slender. They can buckle. And if the buckle is excessive, they may have plastic deformation. So the design of the material is not trivial one. Okay, the other way. This is another thing that I showed last year. This cardboard. Cardboard also is a metamaterial, as a corrugated cardboard. If you make compression tests on cardboard, you will have something like this graph. You can barely see the waves buckle one after the other. There is a movie that, of course, doesn't work. Okay, doesn't matter. But the important thing is that, for instance, this is a test on cardboard. It's a bending test on cardboard, made with that machine. And with this test, they design boxes. So it's a very important test. When you do this test, there is in the middle there may be buckling of the waves. So what that means that the internal structure undergoes some damage, although the whole structure is not damaged. The other way. This is another example. These are containers. After 25 years, I guess, containers that cannot be used anymore. All the harbors in the world are full of these containers, and they are trying to use them for civil construction. In the States, they have building 6-7 floors made with this container. The wall of the containers, we can see nothing, but is a corrugated surface, very, very thin. So what you do if you want to make an analysis, you make some homogenization. These two figures are just example of homogenization, but you can have local buckle. Local buckle, especially in some points. So you have buckle at the small scale or at the large scale. Okay, now some background. Whenever we have damage and we use first gradient theories, we know we have a lot of troubles. We have localization, stable material response, and for instance, it is well known that in a finite element you have mesh dependency of the solution. Gradient plasticity and gradient damage has been proposed since long time for regularizing these problems. These are some of the hundreds of papers have been written on the problem, and the earliest model added gradient of the plastic or the damage variable. But in the end you come out with a equation like the one which is the bottom we took from one of your papers, which is the evolution equation for a damage internal variable. And there is a gradient of it inside it. This is a diffusion type equation. That's why it avoids this avoids localization. But you have an additional field equation to solve. That complicates the numerical solution. Besides, you have a not clear boundary condition that have to be applied. That Luca discussed yesterday. So now I come to with this motivation I come to the model. Just again, it's not that this is an idea of a structure that can simulate something like the corrugated cardboard we saw before. So something that have between the layers and internal elements that should be here. You can see, but I have some here. If you make a simple homogenization you got from 1D homogenization, you get with an equation like this one, which has a non-local term. These two coefficients can be correlated to the stiffness of the long trusses or the short inner trusses. Either one of the two can buckle. So you can have that either one of these two coefficients can become negative if you assume like a simplified constitutive equation for buckling. And so that's comes out the idea of the model. The model is first of all the assumption, the restriction. I present the model only with small displacement and strains. I know that Professor Bertrand said this is a strong limitation. I agree. As should be. I present only linear elasticity, only for the isotropic case. I use the standard generalized material model of Germain. So now no Piola this time, but French school. So the idea is that all the state variables of the model are clearly stated, and each state variable has a non-local counterpart. So I have to read because the screen is not clear. How does this work? Okay. We have the strain, the gradient of strain. Then we have this is damage variable, and a second the several gradient damage, which is not the gradient of the damage value. It's an independent variable. An internal variable responsible for hardening, and another variable responsible for non-local hardening, which is not the gradient of the first one. And then we might have entropy, but it is not, the model here is completely isothermal. The first one had the idea of splitting the variable was probably Golagonyu in 1997. However, he used then just one variable for softening or hardening. All these variables have a dual counterparts, so that the duality product in the prop space gives the internal power. And in here the power, the mechanical of the mechanical variables, which are the dual of the deformation. So the stress I call sigma, the hyperstress I call mi. Then there are internal variable thermodynamical forces dual of the hardening variable I call chi. Some internal forces dual of the damage variable called zeta. You cannot see them, but anyway. All these dual products of the internal variable of damage and hardening are zero, because in the finite volume this work has to be zero. Since I am in small deformation, each kinematic variable is additively decomposed in the sum of the elastic and the plastic parts. So these all strain, gradient of strain, local hardening variable, non-local hardening variable, local damage, non-local damage. All are decomposed in the sum of or in the sum of an elastic and the plastic component. Then the model is completed by choosing a functional of internal energy, and which is functional is a stored energy, so the functional only of the elastic part of the kinematic variable, and the functional of dissipation, which is a function only of the plastic part of the kinematic variable. Then I will not comment on this. We go through the first principle of thermodynamics, second principle of thermodynamics, and we get up with the Clausius-Duhem inequality, which is the one at the bottom, a reduced Clausius-Duhem inequality. And then we can make some constitutive assumptions that comply with those inequality. And the assumption, the internal energy is split in the sum of an internal energy that function, this is strain energy, it's a function of the deformation, gradient of strain, and damage. Both damage variable. This is an hardening internal energies, function of the hardening variables, local and non-local, and both damage variable is one missing here, okay. And case is also an interpretation of the model. Very realistic. Easily removed, splitted in some, introducing two variables, one for if the trace of the deformation is positive, the other one is negative. It's easy to do. It's more realistic to have an anisotropic damage variable. Anyway, it's not done that. Here there are the function. These are an indicator function because this variable has to be greater than 0, cannot be smaller than 0, so it's a unilateral constraint. These are the constitutive equation for the stress, the upper stress. This is the dual thermodynamical force to damage, which are energy release. There are other two equations that we not written for the thermodynamical forces dual of the hardening variables. I assume that the stresses and hyperstresses and the other thermodynamical forces are uncoupled. This is not necessary, but it's common assumption. Then constitutive assumption for the dissipation. Well, I do not go through the details. The important thing is that dissipation has to be taken homogeneous of degree 1. If it is, in this case, we have implicit plasticity. If it is homogeneous of degree 2, we have some time effect. So it can be taken, so it can be chosen, of course. I take this one is implicit, and this other hypothesis guarantees associated plasticity. The fact that, okay, you can't see anything, anyway, with this hypothesis comes out that the dissipation is the support function of a set, and this set turns out to be the set of admissible stresses. So everything like in standard plasticity, and this is very convenient. Drucker postulated holds. Of course, the second principle of thermodynamics was fulfilled since the beginning, and the and the flow rules are given with the classical Kuhn-Tucker, with classical Kuhn-Tucker conditions, like a gradient of some function that defines the set of admissible stresses. But when I say stresses, I will say is a stress, hyperstress, damage, release, so the energy release for the first and second gradient, and the thermodynamic kinematic variable. This would be a sketch. You can imagine this domain in a generalized space of all forces. There are two examples of this function. This would be a nil function in 1D case that couples only for plasticity, that couples the stresses, hyperstresses, and hardening variables. And here is a parameter C that weights the first and the second, the weights the local and non-local distribution. This would be a damage function. So it means that a combination, in this case linear, of the first thermodynamic forces and the second damage thermodynamic forces should not exceed the threshold, which is the correlated fractional energy. Okay, if you write the evolution equation in the rate form, turns out either for if you have plasticity, now I will consider separately the case of plasticity and damage, with a more clear, but basically things are similar. So either in either two of the cases, even though the elastic equation were uncoupled, they become coupled. So when you have nonlinear evolution, there are these coupling terms that come out, that appear. This coefficient D at the denominator has inside this term, which is a scalar. This is an effective hardening modulus. It can be it's interesting because it appears the hardening modulus for the local and for the non-local stressors, and according to the sign of the two, the sum can be positive or negative, or it depends. It's not what is important is the combination. I've done some localization analysis in the case of plastic. It is easy to do in the case of only plastic deformation, from which it appears that plastic deformation do not, plastic strain do not localize, but do not comment. Then just some very simple numerical application to see what happens. 1D. I've done it with spline because we need high continuity, third degree splines. I studied this example, the classical axis extension. This is in the case of plasticity. This is the solution with the first order, first gradient deformation only, and it's seen that as in this case, everything is homogeneous. In order to have plasticity, you need to introduce a small defect. But as the defect becomes smaller and smaller, this solution goes back to the elastic branch. If you add second gradient or strain gradient, the solution is no more homogeneous. This is the stresses along the bar as a function of the internal variable. This is the hyperstress, and this is with the yield function I showed before. According to the value of this weight, you can have that either the end of the bar or the last end of the bar, the first end of the bar, you can have that are the first one to yield. So in the second end of the bar, the first gradient solution dominates in the second end. In the first end of the bar dominates the hyperstress. This is will not comment. This one is some results. This is the second gradient model, elastic plastic solution with uniaxial extension. And these are second gradient dominated solution. That means in the yield function, the contribution of the hyperstress weighs more than the contribution than the first stress, the first gradient stress. All these cases can be obtained with different combination of the hardening modulus of the first and second gradient, say, part. You can see there are some cases that are both negative or both positive. For instance, for this one you have one negative and the other one positive. Still the slope is positive. And can see nothing, but what says here that in any case the plastic strain is does not localize in one single element. In this case, plasticity starts in this on the first end, then the other end starts to plasticize. And this is the analogous result for the first gradient dominated solution, which again with a number of these are non-dimensional values, non-dimensional with respect to the elastic modulus. And also in this case, it is, maybe you can see better here, this is the cumulated plastic strain. And there is another plot I didn't show, but for the cumulated second gradient plastic strain. This is the case of damage. This is the solution for the 1D bar with first gradient deformation only, which is strongly dependent on the size of the defect. And you have also this very sharp snapback. These are the distribution of the release energy forces for the first and the second gradient along the bar. Also in this case you see that according to which one is prevailing in the yield function, we will have damage at the second end or the first end of the bar. And there are some numerical solutions obtained with the damage, with the pure damage model for some combination of data. In any case, we have very sharp snapback. I didn't normalize the threshold, so we have different threshold, but okay, I should have probably normalized it. It would have been better to see. There are some kinks. These kinks are numerical. That means that this happens when the damage is very sharp. So when there is some Gauss point that is activated, we have kinks in these curves. So I have to do. These are very few elements, 30 elements. These are 16 elements. There are many sharp. Many. If I put more elements, this of course this disappear. In any case, I have a step back, so I have to use arc length in order to follow the solution, except some cases. For this one, for instance, I don't have step back. Even in this case, again, you can see nothing. This is the accumulated damage along the bar. So damage, as we expect, goes to some very high value at the end, and but has spread. So it's diffused along the bar. So we have diffusion of the damage. Okay, so the conclusion. I think I'm in time. I will just discuss this point. I've used two separate damage, also hardening variables that affect the first and the second stiffness separately, and that are not the gradient of the one of the other. So they evolve separately, and they evolve with the flow rule. So they can be solved locally. Numerically, they can be found at the Gauss point only. So the non-locality is an equilibrium equation only. All constitutive equation is local. So it's very, very convenient. It's solved in a standard way, as we do with plasticity. Okay, there are some certain number of limitations. Okay, there are open problems. Okay, extension to 2D and 3D. It is very easy to do in the case of isotropic damage. We have already done it. Of course, I didn't show the result because we are working on some example. But it's not easy in the case of plasticity because we have to choose a proper domain for the hyperstress and for the variables for the non-local one. So this is something that has to be discussed, how to choose it properly. There are problems we are working on now when you have complex geometry, because we need numerically G1 continuity between elements, or even with NURBS. We have G1 continuity within the patch but not on the boundary. For in this case, where the parametric lines are not continuous, and so we have proposed a solution that we have submitted the paper for plate, but we are working on this problem also with the plane strain. Okay, thank you.
And you have introduced this N1 and N2 power law type of model in your damage modeling.
Yeah.
Is there any hidden benefit of using it, or is it just a model that you try to find out if N1 and 2 is doing something?
Did you say?
Do you have a hidden benefit, like a numerical benefit, it is easier to solve, or is it just a model?
Well, it's the easiest one, actually. I've said that, that this coefficient have to be strictly larger than 1, otherwise the equation the constitutive equation cannot be inverted. Okay. So that will be strictly larger than 1. The smaller they have, the sharper is damage. So if they are large, damage is softer. Okay. It's always difficult to set. So it's the easiest way to do it. Typically we take 10 by 2, 1.52, and then you should fit it experimentally. And you can also take it then differently for. I took it different actually for first and second gradient, and you could also take it different for the damage affecting the elastic coefficient and the hardening coefficient. But when you go in plasticity, the parameter just explodes. So, yeah.
What kind of arc length method have you applied to overcome these sharp corners?
Well, no, the arc length is very simple. Actually, no, this is a trick. Actually, I've been serious because I did the simulation with the arc length, and then I found the results. I checked that I got almost the same results in many cases. Then I said I follow another way for these figures, because it's, arc length is very tricky to every case you have to change to adjust a little bit the parameters. So this is the another way, like a shooting solution. But I did also with this is 1D case, so it's not difficult to use arc length. 1D, but when you go into this, but with 1D it was not difficult. I checked some of the results are the same. All this zigzag is because the method is not really arc length here. It's not exactly an arc length, because it was quicker to get the solution.
Okay. And why did you get some diffuse damage at the end? This is due to the characteristic length that you used?
Yeah, sure. Yes, sure.
This, it was compared to the sample?
This is non-local. No locality is in the in the equilibrium equation. So the diffusion of the damage is due to the fact that you have gradient in the strain. The strain are affected by damage.
Yes, but the size of the damage zone is related to the characteristic length that you have used. Or is it a spurious broadening of the damage zone? That
No, it's broadening of the damage. Of course, if I use larger characteristic length, I would have even more, even broader, but it's not correlated. The strain is not strictly correlated.
And you pull on it, will the damage zone grow or will it
will
remain concentrated?
No, what do you mean it will?
I mean, if you have localization in a damage zone with finite thickness due to the gradient model, if you
but in this case,
continue loading,
in this case, you cannot. In this example, you cannot have finite thickness because it's homogeneous. So the stress is not homogeneous, but the actual force, the actual force is homogeneous.
Yes, but not the strain. The strain is not homogeneous.
No, the strain not, but the actual force yes. And this is a combination of strain and gradient of strain. So in this case, you cannot get a limited band. It has to spread.
Ah.
So the gradient depends on the internal length, but has to spread. But in all the local.
Oh no. The model remains concentrated. There are different classes.
Well, they have the band. Okay. The characteristic size. This is related to the It's something like
the model.
This is something like that.
Okay.
It's not one-to-one.
Okay. No further questions. Again.